Hello everyone, and a warm welcome to today's Sampe Brazil webinar, Coffee with Science. My name is Dennis Hollein, and I am from the company Evonik Operations GmbH, located in Darmstadt, Germany. I would like to give a presentation on a novel thermoplastic rigid particle foam meeting the fire, smoke, toxicity, and heat release requirements of complex and sustainable aerostructures. This novel thermoplastic particle foam is called raw foam, and it is intrinsically flame retardant. The foam material can be used as a sandwich core for sandwich composite designs or as a standalone material. The target applications of this material are fire-critical applications, such as commercial aviation interiors. Especially in commercial aviation interior components, we have the highest requirements regarding flammability, smoke generation, combustion toxicity, as well as for heat release. And with this overview, I would like to explain the manufacturing route of particle foams in general, especially for Evonik's particle foam material raw foam. The process starts with the preparation of so-called microgranules. These are very small and solid polymer particles which contain every component of the final foam recipe already. These are typically the base polymer itself and other ingredients such as, for example, blowing agents to generate the foam cells in the subsequent process steps. The next step is the so-called prefoaming. In this production step, the microgranules are being preformed to small foam particles which contain a cellular structure inside. In this step, we also reduce the bulk density from, for example, about 700 kilograms per cubic meter down to about 75 kilograms per cubic meter. Ideally, all of those single particles have the same bulk density of, for example, 75 kilograms per cubic meter now. And in the last production step, the actual foam part process, these preformed particles are being processed to a net-shaped foam part, still having a low density of approximately 75 kilograms per cubic meter for the whole net-shaped part. And now let us have a more detailed look into the foam part production process itself. This process step consists of 5 single steps actually. The process starts with the mold closure. After this, we fill in the preformed particles that we have seen on the slide before. And once the mold is fully filled, we can apply the hot steam. This will make the particles expand and fuse together. After this heating cycle, we can start with the cooling. In our case, this is a water spray cooling, which helps to cool down and stabilize the foam part. In the last step, we can demold the net-shaped foam part and use it for further processing, as for example, as the sandwich core. If we have a look to the general market requirements of the aircraft interiors industry, we can see that there are certainly a lot of factors that we have to take into account. Of course, lightweight design plays a major role in this market. Additionally, the used materials have to meet a high thermal mechanical performance due to the highly demanding production and sandwich component manufacturing processes for complex shaped parts. Also, the integration of functions such as inserts is an important factor to enable integrated part designs and to avoid labor-intensive production steps. And finally, there are highly demanding requirements regarding flammability, smoke density, combustion toxicity, and low heat release rates. With raw form, Evonik can meet all of those requirements. And when we compare the state-of-the-art solution for core materials in aircraft interiors, which is the honeycomb, to the new solution of a fully flame-retardant particle foam, we can observe significant differences in many different areas. Most prominent are the increased freedom of part design, the ability to integrate functions directly, and a significantly improved surface quality. We can, for example, avoid the so-called telegraphing effect, which is well known from honeycomb structures and which typically leads to labor-intensive rework of the part. Other than that, the use of foams instead of honeycombs eliminates the need for core fillers and potting materials, which results into significant lightweight potentials for the foam solution. And finally, due to the fact that raw foam is a fully thermoplastic foam, it can be recycled mechanically. We have proven already that the foam can be used in circular economies without losing its mechanical or FST properties. Let us have a detailed look at the typical and challenging FST and heat release requirements of the aircraft interiors industry. The listed test standards are the widely applied test standards for interior components. With raw form, we can easily pass all of those requirements and exceed the limit as specified in the test standard. Exemplary for this, you can see the test specimen after testing for the 60-second vertical burn test, and I also included a diagram presenting the results of a rate of heat release test on the left-hand side. As you can see, all values stay well below the requirements of 65 kilowatts per square meter. Therefore, the test was passed. And building on what we have just learned about the rate of heat release values for the pure foam, let us have a look at the performance when using our particle foam as a core for a sandwich panel. The face layers used here are state-of-the-art glass fiber reinforced phenolic prepregs. We have applied 2 layers of prepreg on each side of the foam. You can see the sandwich panel on the left-hand side of this slide, proving an excellent surface quality with a low porosity of the resin. If we look at the test result diagram on the right-hand side of this slide, we can see that the limit of 65 kilowatts per square meter was not exceeded by each of the 3 test specimens. Thus, the test was passed according to the applicable limits by the FAR test standard. As the next focus topic of today's presentation, I would like to talk about the possibilities to integrate functions such as insert specifically into our thermoplastic particle foam. On this slide, you can see a few pictures of what is possible. These inserts can be made from metal, as it is standard in honeycomb sandwich parts, for example, but they can also consist of thermoplastic materials, like you can see in the middle and on the right-hand side of the slide. These kind of thermoplastic inserts are pretty much new to the composite industry and open up significant advantages when it comes to lightweight designs. Of course, metal inserts can be integrated into the mold directly without the need for any kind of adhesive material. And this slide gives you an impression of how insert integration of standard metallic inserts could look like. In this case, we have integrated a couple of NAS type metallic inserts into a foam sheet by using a simple positioning gauge. These metallic inserts have been fixed inside of the mold by simple double-sided tape for demonstration purposes only. In a real serial production, these metallic inserts would be put on a kind of pin inside of the mold in order to determine the location of the insert and in order to let the foam particles flow around the insert freely. The result is a foam sheet which includes multiple inserts in one production step and without any rework. In our case study around the topic of insert integration, we analyzed for different cases how to put those inserts into a foam panel. We differentiate between inserts integrated into the pure foam and inserts integrated into sandwich panels. All metallic inserts have been included into the foaming mold before filling it with particles, and the thermoplastic inserts have been introduced after the foaming process or even after the lamination of the foam part. On the next slide, we will have a look at the mechanical performance of all these combinations when it comes to their specific pull-out forces. The key findings, as you can see in the diagram on the right-hand side, are that the thermoplastic inserts lead to the highest pull-out forces when testing the pure foam without any phase layer. The main reason behind this finding is the fact that the thermoplastic insert is drilled into the foam with high friction temperatures, which leads to a kind of welding of the insert dome to the thermoplastic foam. When we look at the three variants, including the phase sheets on the very right-hand side of the diagram, there is no statistical difference between the insert types investigated. All variants perform on a similarly high level. All in all, we observed that the failure mode was always the same by a core surface cracking. This is the ideal failure mode for pull-out testing of inserts in sandwich composite components. As an outlook, I would like to gather your attention to possible areas of application for flame-retardant rigid particle foams beside the already mentioned aircraft interiors market. There are also significant potentials in the market for electric vehicles, for battery covers, for example, in the field of urban air mobility for interior components, or maybe for energy storage systems, as well as for railway structures, having comparably high requirements for flammability properties as the aviation interiors market. I would like to thank you a lot for your participation in this presentation about our novel rigid thermoplastic particle foam that is able to fulfill the demanding flame, smoke, toxicity, and heat release requirements of large commercial aircraft. If you have any question about this new kind of material, please do not hesitate to contact us. More information can also be found on our website, which is www.rohrform.com. And I wish you a great rest of your day. Goodbye.